Hello everyone, welcome to my class. Today I'm going to cover double integral in polar coordinates. In our last sections we cover double integrals over general region in Cartesian coordinate. So now today in polar coordinate. So the polar coordinate is represented by r and theta, where r is a radial distance from pole to that point and theta is a angle between radial distance and positive x-axis. And then we have a formula to convert polar coordinate to Cartesian coordinate as well as Cartesian coordinate to polar coordinate by putting x equals to r cosine theta, y equals to r sine theta. And we square and add both sides, so this becomes x square plus y square equals to r square cosine square theta plus r square sine square theta. And you can factor the r square outside, then the inside will be cosine square plus sine square, which is 1. And divide the second equations, y equals to r sine theta, by first equation, x equals to r cosine theta. We got y over x equals to tan theta, and from these relations we can easily compute theta. Theta equals to r tan y over x. And in the double integrals we do need an area element, so area element in polar coordinate will be dA equals to r times dr d theta. In the picture, this r times dr d theta is this region where dr is a width and r d theta is the length. So be careful, we do have one extra r because this region depends on how far from the pole, so it depends on r. So our area element is dA equals to r times dr d theta. Next, if the polar rectangle is defined in this way, for example, r equals to function of r and theta, where r is in between a and b, r is between a, r equals to b, and theta is in between alpha and beta, where theta is this tiny angle which is alpha and theta equals to this big angle which is beta. Then the double integral in polar coordinate template will be, the left side is the double integrals in Cartesian coordinate, and this equals to this domain is from Cartesian's domain to polar region, some sort of polar domain, and double integrals xy becomes r theta and dA becomes r dr d theta. So let's put this upper limit, lower limit, r limit, theta limit. So the double integrals of f of r cosine theta, which is x, replace y by r sine theta, over the integrals over r equals to a to b, integral over theta equals alpha to beta, and r dr d theta. Great. So in general, if our polar region is defined radially simple, means if my radius is in between two functions of theta, and theta is between two constant value alpha and beta, then our double integrals template will be, so I equals to double integrals of f of r cosine theta, r sine theta, and then the integral over r equals to alpha theta, a theta means function of theta, and b will be function of theta, and theta equals to constant value alpha to beta, and the area element is r times dr d theta. So this is the double integrals in polar coordinate template for general r. Great. So a quick note, for the following types of domains, polar integrals are easier to compute: circular domain or annulus domain. Example 0. Let's sketch the polar regions. So the part A, the polar regions are between 0 and 5, theta between 0 and pi by 2, which is the first quarter circle. Let's move on. Part B, the polar region is given the radius between 2 and 3, and theta between minus pi over 3 to pi over 2 is this angular region. Great. Now let's start evaluating the double integrals in polar coordinate. Example 2, evaluate the double integral using polar coordinate, where given double integral is I equals to double integral of x square plus y square over r. That region R is defined as function of r theta, where r is in between 0 and 4 and theta between 0 and 2 pi. So the polar limits are in polar integral, the limits are given to us, so all we need to convert these integrand functions in terms of r and theta. Great. So in polar coordinate, we know x square plus y square becomes r square and dA becomes r dr d theta, and we have the limit of our double integral. So the given double integral becomes, so the double integrals of r and theta, where r limit is 0 to 4, theta limits 0 to 2 pi, and x square plus y square becomes r square times dA becomes r dr d theta. Then we can separate the integrals here. So theta integrals whose limits are 0 to 2 pi, and r integrals whose limits are 0 to 4. So from theta integrals, the theta value is upper limit is 2 pi, so 2 pi times integral of r cubed becomes r to the power 4 over 4, and put r limits r equals to 0 to 4, and put the r equals to 4, so r to the power 4 means 4 to the power 4, you cancel by 1 4, so 4 to the power third. So 4 to the power third means 4 times 4 times 4, so which is 64 times 2 pi is 128 pi. Great. So let's move on. Let's do example 3. Evaluate the double integrals over r of tan inverse y over x dA, where the region r is given this way: set of all xy, where x square plus y square is less than or equals to 4 and greater than or equals to 1, means that's a circle of radius 1 and 2, and then the y is in between 0 and x. So y equals to 0 is x-axis, y equals to x is a diagonal line. So let's sketch these regions. So the sketch of R is given here. So the circle of radius 1 is this inner circle, circle of radius 2 is outer circle, and y equals to 0 is x-axis, and y equals to x is this diagonal line. And we need to find out the double integrals over the shaded region. So let's rewrite the double integrals in the polar coordinate. So in polar coordinate, our r limit is from 1 to 2, theta limit is 0 to pi over 4. So the double integrals is the theta integrals over theta equals 0 to pi over 4, and r integrals where r limits are 1 to 2, and then tan inverse y over x is in polar coordinates simply theta, and the dA is r dr d theta. Great. So then again here let's separate the theta integrals and r integrals. Let me scroll down. So theta integrals, so theta integral becomes theta square over 2, and theta limits 0 to pi over 4. Then r integrals, integration of r becomes r square over 2, and r limits 1 to 2. Then put theta equals to pi over 4 and r equals to 2 and 1, and simplify. Our final answer will be 3 pi square over 64. Great. Now let's move on. Our example 4 is my favorite problem. So ice cream problems. Find the volume of solid that lies above the cone and below the sphere. Solid lies between cone and sphere. So below the sphere of radius 1 and above the cone. So let's sketch the region. So this is a sphere, and the inside is a cone, and we need to find out the volume between below the sphere above the cone, this shaded area or shaded regions. So for our double integral, let's find the cross section first. So the cross section of sphere and cone will be this circle. So we project this cross section down on the xy plane, which is this circle, this dotted circle. So to find the cross section, let's solve these two equations, sphere equation and then the cone equations. So from this sphere equation, x square plus y square and z square and plus this z square values I substitute from the cone z value, which is radical x square plus y square outside square. So this square and radical cancels, so simply x square plus y square plus x square plus y square equals to 1. So the next step, I can add these two, so 2 times x square plus y square equals to 1. Next step, divide by 2, so then we have x square plus y square equals to 1/2, which is a circle of radius 1 over radical 2. So this is a circle of radius 1 over radical 2. So if our domain of integration is circle, then we need to apply the polar coordinate. So let's write our domain in polar coordinate. So in polar coordinates, my radius will be between 0 and 1 over radical 2, and theta will be 0 to 2 pi. Right? Great. So then our volume equals to double integrals, and let me pause for a second and remind you calculus 2. When we compute the area between two curves, then we find the area of the top curve, and then we find the area of the bottom curve, and we subtract the values. We subtract the area given by the lower curve from the area given by the upper curve or the top curve. The exactly same idea here. So double integrals, so the functions coming from the upper curve or the top curve, here the z coming from the sphere is on the top, and then the function, the z coming from the bottom curve or the cone. Hopefully this formula makes sense to you. Then let's put the value. So the z from sphere is z equals to radical 1 minus x square minus y square, and z from cone, which is radical x square plus y square. Let me scroll down, and we know our domain is a circular domain, which is a circle of radius 1 over radical 2. So we are plugging the polar coordinates. Let's move on. So in polar coordinates, so r integrals and theta integrals, where r limits will be 0 to 1 over radical 2, and theta limits will be 0 to 2 pi for theta integrals. Then in the integrand, radical 1, pull the minus out, then x square plus y square, which is r square in polar coordinate, and this is simply r, and the area element will be r times dr d theta. Again, we can separate the integrals, theta integrals and r integrals. So theta integral is from 0 to 2 pi times, multiply this r inside, so r times radical 1 minus r square, which is here, minus r times r is r square, outside is dr. So from the theta integrals, we got a 2 pi. Then we are integrating the first term with u sub. For the second term is easily evaluated. So for the u sub, u equals to put 1 minus r square, take their derivatives, so du equals to minus 2r dr. Then I have r times dr, so that means I can divide by minus 2, so du over minus 2 equals to r dr. Then the integral of this first term becomes radical u, r times dr is minus du over 2, which is here. Okay, so let's continue. So 2 pi, so then the integral of the first terms becomes from here minus radical u du over 2, and then this minus r square integral becomes r cubed over 3. We scroll down, then 2 pi as it is, then the integrals of radical u becomes u to the power of 3/2 over 3/2, so you just flip then 2/3 and 1/2 is I just pull outside, minus r cubed over 3, and let's resubstitute the value of u equals to 1 minus r square and plug the value or plug the limit of r given 0, r equals to 0 to r equals to 1 over radical 2. So 2 pi in the next step I copy as it is, then this 2 cancels, minus 1/3, this u is 1 minus r square and then power of 3/2 minus r cubed over 3, and r equals to 0 to 1 over radical 2. Then put the r equals to upper limit and put r equals to lower limit and simplify. So please pause the video and try to actually simplify this one. So it gives you pi over 3, 2 minus radical 2. Okay, let's move on. Let's do another example, example 5. Let me slightly small, am I missing some? Oh, yeah. So example 5, evaluate the iterated integral by converting the polar coordinate. The given double integrals, we have a Cartesian coordinate, so let's convert this Cartesian coordinate to the polar coordinate. So the important part is you need to look for the domain over which we are integrating. So in given double integral is integral 0 to 2 integral 0 to radical 4 minus x square times integrand function is e to the power negative x square minus y square, and first we are integrating with respect to y, dy, and then dx. So the inner integral is over y and then the outer integral is over x. So from the inner integral, this is the y limit, so y equals to 0 is the lower limit and y equals to radical 4 minus x square is the upper limit. So if you square and rearrange the term, this is simply the circle of radius 2, x square plus y square equals to 4. So draw the circle of radius 2 and then go to the next limit, the outer integrals, which is the x limit, so x between 0 and 2. So then we need to truncate our domain when x equals to 0 to x equals to 2, so that means we are only taking integrals over this first quarter circle. Great. So then we need to convert this to the polar. So in the polar here, my r is going from 0 to 2, and to cover these regions our theta equals to 0 degree to all the way to pi over 2. And also on the integrand functions, we need to convert this function of xy to function of r theta, and we know in polar coordinate x square plus y square becomes r square, and the area element, which is dy dx, becomes r times dr times d theta. Please don't forget this r, which is looks like extra there, but that's a area element. Great. So in polar coordinates, the given xy integrals becomes theta integrals, so double integrals over theta equals to 0 to pi over 2, and r integrals, r equals to 0 to 2, then e to the power negative r square, and dy dx is r dr d theta coming from here. Hopefully this conversion makes sense to you. Great, let's move on. So again here we can integrate separately. So from theta integrals over theta equals 0 to pi over 2 is simply theta, and put the upper limits pi over 2, which is pi over 2. And for the r integrals, it's another good candidate for use of. So r integral is r equals to 0 to 2 times r times e to the power negative r square dr. Then put u equals to minus r square then its derivative is du equals to negative 2r dr divided by negative 2 r dr equals to minus du over 2. Then this reduces to e to the u minus r square u, so e to the u, and r times dr. R times dr is minus du over 2. And the integrals of eu with respect to u is simply eu. N minus 1/2 is a constant here as it is. Great. So now let's continue in the r integrals. So from the theta integrals we have pi over 2, and from the r integrals we convert this to the u integrals, and we have the value here, so which is minus 1/2, and we substitute u equals to again back minus r square, so e to the power minus r square, and r limits r equals 0 to 2. Then put r equals to upper limit 2, so minus half, and then pi over 2 is multiply these two constant, minus pi over 2 times 2 4, e to the power negative, put r equals to 2, so 4 e to the power negative 4, and when you put the lower limit we need to subtract the value, so minus from formula, put r equals to 0, e to the power 0 is 1, so simply 1. Great. And then multiply this minus inside, so that means I'm just switching these two positions here, so pi 4th as it is, then 1 minus e to the power negative 4. Great. So we finished the double integral in polar coordinates. In our next class we will start the triple integral. Thank you.